Thank you very much. So I'm Ryan McMahon from Cambridge Mobile Telematics. We're a technology company that measures driving behavior, and our mission is to make the world's roads and drivers safer. And we do that today, or historically we've done that, by identifying and understanding the risks that create crashes, and understanding what risks go into that crash, and then being able to help and identify how to prevent that is really our core mission. And we do that by understanding and identifying a vast array of sensors and processing that information on AWS today. And for the most part, over the company's history, it's been used on an individual one-to-one basis, meaning that the individual driver is measured and we process that information and provide that information back to them. We also detect crashes, respond to them. But over time, what's happened is that data size has gotten even more complex, because we're gathering sensors as those sensors have come online over the company's history. We started with the initial version of feature phones, have gone to smartphones. We use proprietary tags that we manufacture ourselves. And we're also expanding into other sensor platforms. All that information today is processed on AWS, but it's been processed and used for individual drivers. And the reason that we do this is to identify and understand those basic risks so that we don't get to the top of the pyramid being roadway fatalities. And if you're not familiar, unfortunately, over 40,000 people die on the roads here in the US every year. But even more than that, we're talking about over 1 million people globally, and we're a global company. So over 15 years, our focus has been on individual drivers. So this session is about geospatial, and you may be asking yourself, how does the two things connect back to them? Well, what happened was we started to do research in the topic and identify more than just the individual driver risk. We started to identify a host of features that go beyond the individual driver, because when it comes to crash risk, it's not just the individual driver that leads to that negative outcome, that leads to those injuries and fatalities. In fact, the vehicle has a large role to play, and the road does as well. And we've expanded significantly onto that last phase, into understanding road risk. So the goal is to predict and identify where crashes are going to happen. Because a crash in itself, if we could just simply identify where those serious injury crashes happen and address the issues that were there, then we can remove those fatal crashes from the past. But the reality is that it's not predictive. As sad as each individual crash is that leads to an injury or fatality, in and of itself, it's not predictive to identify where that next fatal crash or injury crash is going to happen. So you have to identify the features that are below that, what leads to the risk, to get to the point to identify where a crash is going to happen. And that's where AWS came into play in a huge way for us, because we're processing this enormous amount of data every day. Over 1 trillion data points are coming in, and we had a problem when we wanted to move to road risk, because for an individual driver, the processing that goes into play is important, but it's not in the same factor from a geospatial perspective. So we had to take 2 steps further to get to the point to be able to identify those issues. And this is what we built. So from this now, and this is an example, this is a road in Arkansas. Just spoke recently at the Arkansas Safety Summit, and their director of the DOT, Jared Wiley, invited me to come and present, and this is one of the data points that I showed. And this is an aggregation of hard-braking events that occur over a month period of time, over a 3 months period of time. And when you look at the aggregation of those events, it becomes clear when you actually start to get under the ground. But we didn't identify this issue from an image. We identified this issue from human behavior. But if you look at the image, it becomes very clear. The stop sign's occluded. So if that stop sign's occluded, there's many branches and trees that are blocking stop signs all over the world, but how many can you get to the point to identify where the human behavior is concentrated and aggregated to get to the point to identify that risk? So the challenge is that if you get to this point, that you have all of this information to identify the behaviors that lead to crash risk, and you can aggregate it together, how do you display it in a map that's useful to the DOTs, to the highway safety offices, to the people in EMS, to get to that point to be able to reduce those risks as they occur? And really the question came down, should we use road segments? Should we take all this information and load it into pre-existing mapping coordinates? And really what happened was we said, we're going to use H3 hexes. But the problem was at that point, AWS didn't support taking that data and moving into H3 hexes. So this is really what AWS has been able to do, is to take all of that information today and give us the information that we need to identify at a massive level. And what we're doing now is loading over 5 billion records every single day into a system that opens up and can do something like this. So this is a stop sign in Washington, D.C. I went there in person, I took this picture, same issue. Same exact issue. You can see that there's a stop sign that's occluded by a tree, and what's happening? Well, people are getting in near-miss crashes. And today, the way that these problems are solved, if you're a DOT or highway safety office, is we wait for the bad thing to happen. Because the currency of risk today is unfortunately the crash itself. So we're moving 2 steps beyond that. And AWS, if AWS didn't have those capabilities, we wouldn't be able to take this massive amount of research that we'd already done in identifying risk and be able to bring it to the solution to make it easy to use. And effectively what I try to term it as is Zillow for road safety, is looking at, from a mapping perspective, how do you identify and understand those risks and make it translatable across the globe. And this is a huge scale of undertaking to identify those behaviors to ultimately get to the point where we can move further down the pyramid. And from a technical perspective, the partnership that we had with AWS, 18 months ago, we couldn't have done this. And it was that partnership that led to this development. So frankly, I'm so impressed, and to talk more about really that work of getting further down the pyramid and how technically we got to that, I'm gonna hand it over to Ravi from AWS.
Thanks, Ryan. So as you heard, thank you. Redshift went down the path of building spatial capabilities into a cloud data warehouse. We went down this path some 7 years ago, 8 years ago, and we're pretty far along now. And the key to what CMT, Cambridge Mobile Telematics, has built into the Street Vision platform is using the spatial data together with the spatial query functionality with Redshift. So you don't need to learn anything new. It's all done in SQL, right? So you have all the spatial capabilities, and I will talk about some of the newer capabilities we've built, which is specifically the H3 functions, the hierarchical hexagonal indexing, which is an open source initiative. It started at Uber, I believe, but it is a huge leap in terms of spatial performance, right? So the question on top of all of your minds is, why Redshift spatial? All of you probably heard of Amazon Redshift, one of the first cloud native data warehouses to be released almost 14 years ago. The reason is very simple. Redshift has the right architecture to do massively parallel processing, MPP architecture from day one, right? It's the first cloud data warehouse to be built on MPP architecture. It can handle petabyte scale data, and it operates on columnar data. So you get all the benefits of columnar data, your vectorized scans for really, really efficient query processing on read queries, and that lends very, very well into petabytes of spatial data. The volume of data that CMT has to deal with is massive, right? It's in the petabyte scale. So couple that with the highly precise, numerically accurate robustness of our spatial implementations, whether it's WGS 84, the SRS standard, for implementing spatial projections on an ellipsoid Earth model, and leveraging all the functions that we're continuously adding to our spatial portfolio of functions. The most recent of which is the H3 functions, right? And those who are familiar with PostGIS libraries are probably already familiar with some of the spatial capabilities in Postgres-like databases. So we follow the same syntax, the same sort of functional equivalence. So when we first embarked on this, we launched geometry data type as the first class data type in Redshift. And very soon, a couple of years later, we added geography as well. So geometries are more for 2D, two-dimensional, and non-geoid based, so latitude, longitude based coordinates for short dimensions where you don't need the projections and accuracy, numerical accuracy of geography data types. So together with geography and geometry as native first-class data types in Redshift, you have the building blocks to handle all spatial data in Redshift. And then we're now up to over 100 plus functions, spatial functions, implemented natively within Redshift. And most recent of which is the H3, and I'll talk about H3 in a bit. So here's what it looks like when you run a sample query in Redshift, right? So it's pretty simple. You create, just like any other cloud data warehouse, you create a table, you load some spatial data, and you use SQL to query it, right? And you use all the built-in spatial functions, all those 100 and plus functions that I talked about. And voila, you have your spatial analytics capabilities. You can mix and match spatial data type, non-spatial data types, like anything else. So this is pretty much standard now. Many cloud data warehouses support it, but Redshift, with its architecture for very high performance, really excels in processing spatial data. And what's special about the functions, the spatial functions, is that, for example, you can do these kind of visualizations. So what you're seeing here is, let's say this is a map of Berlin, and let's say you basically want to, let's say you have a table called accommodations with all the coordinates of hotels in that polygon. Those little clouds that you see are the perimeters of the polygons, and the query here is basically showing you, find me all the hotels in that polygon, right? So that's, you submit a shape file, and you extract the latitude, longitude, and you simply use a regular SQL query, and that's it. You get all the list of hotels. So this is a very, very simple query, but think of it as the building block for processing at scale, millions and millions per minute, or per second in some cases, right? So that's the scale with which it operates. And some of the spatial formats, you obviously see the shape files there, but we also support WKT, it's well-known text, WKB, well-known binary, and the extended versions of those, WKT and WKB, and GeoJSON, and many other types. So we have a lot of flexibility in terms of reading and writing spatial data formats. And this is, I don't want to, you can look up the docs here, but this is some of the sample of the 100 plus functions that we have, and it's continuously growing. What you see on the yellow or orange there is what we've recently added. We started with the 5 functions that are most needed by their street vision application. There are several more H3 functions, and we plan to introduce them, but this is where we started, right? So the question is, what is H3, right? So H3, as I said at the start, is a hexagonal hierarchical indexing system. The big problem, as you saw in a couple of slides ago, is the old way of querying things. You have a polygon, right? You define a perimeter, and you want to find points within that polygon, or some other variations of it. So what it boils down to for the SQL engine is a Cartesian join, basically, which is complex, expensive, and exponentially huge, right? So it can get bogged down. With H3 indexing, you have pre-computed indexes for your locations, right? So each index, each cell's index is the location itself. And you can choose the resolution that's of interest to you. There's 16 levels from 0 to 15, and you can choose the resolution that you want. So a lookup is lightning fast. To see how fast it is, here's a comparison that you will see. You can save 98% of compute. the old way of doing lookups versus the new way of doing lookups, right? And this shows you some of the other resources as well: memory, CPU time, et cetera, and query response times. So H3 is a game changer for spatial lookups at scale, right? So you can save like up to 85% on your Amazon charges if you want, your Redshift charges, but just by using H3. Okay, so some of you may be wondering, we talked about spatial. Ryan talked about the Street Vision platform in CMT. So how does it fit into some of the NLP capabilities? He talked about, they're using Bedrock and some of the models that Amazon has. The way it all fits in is through query editor. Amazon Redshift has the query editor, which is our SQL IDE or SQL interface, if you will. It's been growing in features. We now support Jupyter-style notebooks for SQL, and it has full integration with Amazon QSQL, which has integration with all the models that Amazon has access to, both Amazon developed and third-party models. So what this gives you is the ability for non-SQL experts to be able to use a SQL data warehouse like Amazon Redshift using plain English, natural language processing, right? And the big advantage, you might say, is why should I use this engine versus many other query engines that are also NLP capable? The biggest advantage is that Amazon Query Editor v2 is fully integrated with the Amazon Redshift Cloud Data Warehouse. So you have full query history, full metadata, and you have full context of the schema. It does the schema crawling, it understands what you're trying to query, what tables and columns, and it understands from your query history exactly what you're looking for, right? So that is a huge difference. And some of the other query tools within the AWS portfolio, like QuickSight, are also building this integration with Redshift. And finally, generative SQL. So translating NLP, your NLP in plain English, the intent of your query is where the generative part comes in, right? It looks at your history, like I said, but it also divines your intent, right? And this is where it really is a game changer, because it can sort of do predictive queries, and you can of course have the ability to edit it in your notebooks, right? It generates the query, you can execute it as is, or you can edit it and submit it, right? So that is one of the biggest advantages of generative SQL integration. And finally, as I said, I think I've already mentioned some of these things, but the biggest advantage is it understands the context of your schema, the tables, and the layout, and the history. Taking those two together is really the big difference. If you use a third-party BI tool, you will be missing some of that context because they don't have the level of integration that we do to our own metadata, Redshift metadata. So that is the real differentiator. So with that, I'd like to thank you folks for taking the time to attend today. And we have a few minutes left here, and I will open it up for questions if any of you have it. We will take questions for Adrian from Cambridge Mobile Telematics, Ryan, or myself. I'm from Amazon Analytics team. So more than happy to take questions. Thank you again for attending today.